In this lesson, we shall focus on applied mathematics, shooting and finite differences methods. We shall look at the differences between these methods and the applications. Question 5, compare briefly the shooting method and the method of finite differences in solving boundary value problems by stating the main advantages and the main disadvantages that are involved here. And obviously, this is rather very, very interesting thing we need to do. And so we're getting started to deal with this particular, to answer this particular question. Okay, so you'll remember this by and large, but we recap because it appears in several papers. The notion of the shooting method coupled with the finite differences method. Finite differences method. So you would have the positives, right? The positives are that certain to give or to yield a solution. The shooting method is certain to give a solution. Even in the nonlinear case. In the nonlinear case. But however, we agree that the downside of this, we saw it before, requires more computational effort. Requires more computational effort. The advantage of the finite differences method is that it requires less computational effort, like we've seen, so it requires less computational effort. Some of these I'm sure you'd remember from our previous discussion, especially when you are dealing with the higher order systems. So it requires less computational effort, as we said, especially for higher order. For higher order. Especially for higher order systems. There's less computational effort, especially for higher order systems. Right, so that's something you need to take note of. Okay, there's more to this to say, may not converge. These may not converge. That is, if the equation is nonlinear and the initial estimate and the initial estimate right, and the initial estimate is not good. It's not good. This method of finite differences differs from the shooting method because of this. But we said the advantages of the finite differences method is less computational effort, especially for higher order systems. The shooting method obviously is certain to give us a solution in the end of the method. We saw that we actually went on to use the average interpolation formula to actually get a solution in the case of the shooting method. But obviously, the advantage, therefore, the downside of the shooting method is therefore that it requires more computational effort, whereas the finite difference method may not converge if the equation is nonlinear and the initial estimate is not good. So those are the things we actually need to take note of. We proceed to the next question. We proceed to the next question. We proceed to the next question. Right, so we proceed to the next question as follows. Right, so obviously as we look at this particular problem, the finite differences methods are methods that are of great interest to us. And now let us look at this particular problem here. And this one is one of the exam questions that appeared in October, November. So this one appeared in November 2023, this question. Let us spend some time on this question and make sure that we are able to sort of make sense of it and interpret this question very, very well. And now we are then obviously looking at how to actually obviously get started. Set up the system of equations. Here we're going to use the what you call the octave. We're going to use octave here. As said already, octave is one thing that is a tool that can be used from time to time to help in solving the problems, because sometimes the solutions are long and therefore we might decide, okay, let us not continue, let us not solve. Like here, they said, do not solve the equations. So obviously by hand, they will say, do not solve the equations. But if we are to solve the equations, then software becomes useful, and octave becomes very, very useful. So we start as follows. And this becomes how our solution begins. Right, and we say the following: let x sub I denote the grid points H, which is minus xi, and let yi denote the approximate value. Okay, so we're going to let xi, we're going to let x sub I denote the approximate value, right, of, now we're going to have x t sub I. We will use the following. The following approximations. Shall use the following approximations. So the approximations would be, so this one here, for example, because we are dealing with this, how will these therefore be important to us? So we actually know that whenever we have d squared x dt squared evaluated at t equals ti, which is xi 2 xi, you divide by h squared, divide by h squared. So this would be the formula we're going to use, because we're seeing the second derivative. So for the second derivative, dx squared dt squared will be approximated by this, with x evaluated at t equals t sub I, which should be approximately x sub I. Right. And of course, if you have t evaluated at t sub I, which is t sub I. Thus, but I want to also state something here. Moreover, when we're dealing with this second derivative, we're gonna, like the first derivative, x prime at 1. We need to note that whenever we are dealing with dx dt evaluated at t equals t sub I, this is x I plus 1 x. Okay, so this one is going to be exactly x subscript I minus 1 divided by 2h. Divide by 2h is a difference equation. It's a difference equation. It's a difference equation, whereas simultaneously this one is also a difference equation. Right, so this one is a difference. It's a difference equation. Okay. So we continue as follows. Right, we continue then as follows. So now we need to write the difference equation for this one. If x double prime is tx, this actually would therefore imply the following. If this is the case, it will then imply the following. It then implies that you would have x, according to this, x double primed is going to be xi plus 1 minus 2x subscript I plus x subscript I minus 1 divided by h squared. So now you'd have t subscript I, x subscript I, according to this. Okay. But by the method of finite differences with delta t equals 1 when delta t is h equals 1, we get. So we're going to get, so we put 1 here. So it's going to be x I 2xi. So we have this. So you'd say the grid in this problem consists of the following points. So we need to deal with the grid for this particular exam question. The following points. Okay, so what are the points? Let us deal with the points. Because right now, would have that delta t is 1, there's x1, and then there's x3. So if this is the case, it would mean that the grid will contain the following points like t0. So it will contain like t sub 0, which is occurring there, which is 1. T sub 1, you add a 1, you get a 2. You add a 1, you get a 3, which is this. So those are the grid points. Those become the grid points. So now at this point, what we're then saying is x subscript I plus 1 minus 2xi plus xi minus 1. And this is equal to t sub I x sub I with t0 is 1, t1 is 2, and t2 is 3. Okay, check that. And then there's more we need to deal with here. So at this point, we will have exactly the following. So if we have up to the t's like that, you then be in a position to have the following analysis of this, which means that whenever I is 1, right, you'd have exactly the following here. You'd have exactly the following. Right, so this equation is normally called star. And then we then say the application of star okay, the application of a, I'm going to say, you see, the application of a, of these grid points so the application of star, that's what I'm saying, at the grid points. So we say we apply star at the grid points. So the application of star at T0 is 1, T1 is 2, T2 is 3, gives the set of equations. Gives the set of equations. Gives the set of equations. Let us give the equations. When I is what? When I is 0, you would have x1 minus 2x0 plus x minus 1 equals, when I is 0, t0 x0. When I is 1, x1 x0 t1 x1. When I is 2, 3 x2 x1 t2 x2 when I is 2. Then we stop here because we are going up to these values, up to the t2 there. And now we will actually stop at this point, meaning you'd be having the equations x1 minus 2x0. Right, so we have the x1 minus 2x0 plus x minus 1 is t0 x0. x2 minus 2x1 x2 minus 2x1 plus x0 is equal to t1 x1 x3 minus 2x2 minus 2x2 plus x1 is equal to t2 x2. T2 x2, like so. Okay, but now we need to explore this one. We need to explore that. So we have so if then you have this one is like we have said that T0 is 1. So you would remember what we said here. Right, what we said here. The x at Ti is Xi. All right, so this is x at Ti becomes Xi. So which means that x at T0 is going to be X0. X at 1, which is T0, is going to be our X0. Which means that this is like X0 is equal to X0 primed. Okay. Which then means that we remember that the dx dt evaluated at t equals ti is x I plus 1 minus xh. So now let us examine this here. So this one, according to this, it's going to be, if you put 0 in the place of I, it's going to be exactly x1 minus x sub minus 1 divided by 2h. Like that. So that, according to this constraint, and therefore this is x0, x1 minus xi minus 1, then you have 2 by 1, which is delta t equals 1. So which means that x0 is x1 minus xi minus 1. Okay, let's continue. We continue. Right, continuing would have, so this particular differential equation can be written like this. So now let us check. So we're going to use it together with the other conditions we have. Let us look at this one. T0 is 1. T1 is 1. T2 is, okay, T0 is 1. Then you add 1. If you add 1, you get a 2, excuse. You add 1 plus 1, you get a 2. So you add the delta t. So you have a 2. And then you add 1 to 2, you get 3 because you're adding 1. The step size is 1. Okay. So now with this mentioned, we'll be able to continue with the following. You're able to continue with the following. Okay. So obviously at this point now, what is this? X3. So X3, our 3 is T2. So it's going to be X at T2. But according to this, we have said, so we have that x at ti is xi. So this would mean, therefore, x at t2 becomes x2. X at t2 becomes x2. X at t2 becomes x2, yeah? Which is equal to 0. Okay. So x at t2, you can call it x at 3, which becomes exactly a 0. Like that. And so this means that x2 is equal to 0. Okay, I mean, what is the importance of these things? So we need to take these blue equations, and then use them there. Let's take the blue equations. Okay, we're going to use the blue equations on the other side. We're going to use the blue equations on the other side. Right, so you have the following, which is 2x0 plus x minus 1 equals t0x0. We need to simplify these equations, and then we're going to use octave to solve. Right, which is x2, then we have minus 2x1 plus x0 is t1x1, x3 minus 2, x2 plus x1 is t2x2. So now let us substitute everything we've got. We have x1, but what is this? This is x1 minus x subscript minus 1. You can use it here. Okay, but the objective of this is to remove the negative subscript. So which means that we can say x subscript minus 1 is equal to what? It's equal to x1 minus x0. That's what we're going to use here, which means x1 minus 2x0 plus the x1 minus x0. What is t0? What is t0? Okay, we write the list. We said t0 is 1. Then t1, you add delta t there, you get 1 plus 1 is 2. T2, you add 1 to 2, you get a 3. So that t0 becomes a 1. So this is going to be 1 by x0. Right, so it becomes 1 by x0, giving us and therefore just x0. There. We're going to simplify this. So we have been able to remove the negative index there by virtue of this condition. Then we're going to use our octave to solve this system. x2 minus 2x1 plus x naught. What is t1? It is 2, which is 2x1. Then we have x3 minus 2x2 plus x1. What is t2? It is 3x2. This is what we have. Okay, let us perform some simplifications here. So now this one, if you check, okay, you take a deep breath and analyze this system, then you need to be able to get the answer to this. But yeah, let us ponder on this one a little bit and see what we've got. And see what we have got. And see what we have got. Right, and see what, okay. Because this one now is going to be, yeah, it looks like a homogeneous system. Because you have x1 plus x1, which is 2x1. And this is minus 2x0 minus 2x0, which is minus 4x0, which is minus 2x1 and then you can write, okay, in any order with the x0. Okay, so it's minus 2x1 the x0. And then there is an x2. You can write x2. And this is equal to, yeah, the x1 minus 2x1 minus 2x1 is minus 4x1. So you can put a minus 4 here. Right, you can put a minus 4 here. Because now we have minus 2x1, but minus 2x1 is minus 4x1. Then there's an x0 plus x0. Then there's an x2, which is 0. Okay, let us check more of this. So this one here, any like terms, are these two. So you can write x1 minus 5x2. Right, and then plus x3. So this is what we have, which is 2x1 minus 4x0 minus 4x1 plus x0 x1 minus 5x2 plus x3 equals 0. How many unknowns are here? So yeah, this is what you need to think about. Then you think about the unknowns. Okay, yeah, but there's something more we can do. Like, we got that x2, according to this, x2 is equal to 0. x2 is equal to 0. So you have this with x2 equals 0. If x2 equals 0, you have 2x1 minus 4x0. x2 is 0, which means you have minus 4x1 plus x0 is 2. Then x2 is 0, which means you have x1 plus x3 equals 0. Okay, we need to solve this system. Then we must find the values that we want. So we have, therefore, 2x1 minus 4x0. And then we have minus 4x1 plus x naught plus x1, or x1 plus x3 with x2 equals 0. With x2 equals 0. Obviously, we have used that condition, so we can delete it. We can delete it. So now we need to get x1, x0, x3. But let us write it properly. Okay, so that we can use octave. Yeah, but this one is a homogeneous system. Right, it is clearly a homogeneous system. We expect it to have a trivial solution. We expect a trivial solution. Minus 4x0 plus 2x1 0x3 0. x0 minus 4x1 0x3 equals 0. 0x0 plus x1 plus x3 equals 0. Okay, yeah, let us take a look at this one. Let us take a look at this one here. Let us take a look at this here. Let us take a look at these. And now we need to solve this. Then you can use octave. We can use octave to solve this one. So let us practice with octave. But before we switch to the octave panel, we note therefore that this is going to have a matrix minus 4, 2, 0. You can factorize it. So we're going to use the matrices to deal with this on the octave panel. Then you have 0, 1, 1, x0, x1, x3. 0, 0, 0. So you're going to have this. It's a system. It's the matrix. This is the matrix equation. This becomes the matrix equation. Matrix equation. This becomes the matrix equation. And so with this, then we continue to actually solve this using the octave system. Using the octave system. So now let us use octave to solve this one. But now, if you look at these carefully, can it be solved? It appears that it can be solved. So let us continue with octave. Let us continue with octave. I'm going to close this one. Close this, and then we're going to open the octave panel. Let us open octave. Right, so this one is octave. Now, if this is octave, of course, you need to remember what we had before. So now remembering what we had before, we actually have the following matrix. Let us memorize it. Let us memorize it. Let us memorize it. Zero, 1, 1. X0, X1, X3. So you have this. Okay, you need to memorize this matrix because this matrix now is the matrix we need. But it's an easy one to solve, obviously, but yeah, we're going to practice with Octave. There's a matrix we're going to call matrix A. And then it's going to have -4, 2, 0, 1, -4, 0, 0, 1, 1. Okay, now this is the matrix, which is -4, 2, 0, 1, -4, 0, 0, 1, 1. We find the inverse of this matrix. So we're going to say, let's define a matrix B, where B is the inverse. We define the matrix B, which is the inverse of the matrix A, like that. So in other words, the inverse of the matrix A is this one here with the decimals. Now we define another matrix we call matrix C, which is the column vector, which is 0, 0, 0. Then we have the zeros there, okay, which is the column vector we saw on the far right of the system, okay? So if this is the column vector we saw on the far right of the system, we'll then continue and compute the solution. The solution is going to be B, the matrix B star C. Obviously, as I indicated, that this is going to possibly have a trivial solution, so that there's a trivial solution to the system of linear equations. And therefore, we have the following. But then in the end, it's 0, 0, 0. So that, according to this, we have already solved this particular system. And then what we are seeing is therefore that x0, x1, x3, octave is giving 0, 0, 0. So this one is an octave solution. So we're therefore getting that x0 is 0, x1 is 0, x3 is equal to 0. But x2 is also 0, we remember. So we can then say hence x0 is 0, x1 is 0, x2 is 0, x3 is 0. Okay. So this would be the solution to this particular problem of finite differences. We have used octave. Octave has been used to solve the linear system. So In the exam, they said do not solve this because maybe to take some time. But now with us, we have been able to use Octave to solve this system. Okay, so obviously we shall look at other Octave algorithms that can be used to solve a wide range of problems. A wide range of problems that we need to learn. So now we continue with our approach in our attempt to solve more systems. Okay, so in the next 1 minute, I will continue. I want to connect the power because I'm expecting load reduction at 5. So I'm trying to get the system prepared for that. I'm trying to get the system prepared for the load reduction in the next 9 minutes or something like that. So, and then we're going to move over to the next question, but I'm trying to get my network secure with reserve power. I'm expecting I received the notification that we might have load reduction. Might have load reduction at that. So we will, right, we must have load reduction at that. So we'll continue. Right. So we continue. Yeah, we'll continue, please. Just I'm getting my system up and ready for the power cut that might happen at 5. I don't want it to affect our network, so I'm trying to make sure I have a network that is in reserve for this. So okay, good things. I'm trying to get my cables connected because the power might just zip and go at 5 o'clock. For the next good number of hours when the load reduction will happen. So I'm trying to get the power, the network, so that the network might not go. There might be a slight network interruption now, but it's not going to be permanent. It's just going to be like 1 second and then it's restored. It's going to be like 1 second and then it is restored. Then we shall look at the next problem that we need to practice with. Shall look at the next problem that we need to practice with. We need to look at the next problem that we need to practice with. Right. Expect a slight interruption for a second or something, or a split second as I transition from one network to another. So, but it's not going to be for very long. Right. The system is able to catch up. Right. So the system is able to catch up. Right. We're right back again. Right, so that's fine now. I'll just transitioning to my network because when the power goes, I know I'm going to be in the dark. So when the power goes, I know very well that I'm going to be in the dark. So I was preparing for the power cut that is going to happen because I received a message. So I was trying to connect to to my alternative network because in 4 minutes the power will go. Okay, now we continue then with our analysis of problems. Let us look at another problem. Let us look at another problem. I want to actually have another problem. Right, we're going to have another problem. Another question, that is. Okay, I'm trying to get to another question. All right, I want us to look at the Adams-Bashforth. Okay, the Adams-Bashforth is part B. But before we look at the Adams-Bashforth that appeared in November 2023, I want us to look at the following. All right, I want us to look at the following. Okay, let us look at this particular question and then just practice with it. It came in the November 2023. Let us practice with it and see exactly what needs to happen here. So in this case, we are dealing with this kind of a question. And right now, you need to find the Pade approximation R3 of x with numerator of degree 2 and denominator of degree 1 to the function f of x equals x squared plus x cubed. Right, so we need to note, therefore, that to find the Pade approximation R3 of x, we note that the Pade approximation right, so the Pade approximation, right, the Pade approximation is, right, so now with the numerator of degree 2, denominator degree 1. So numerator of degree 2 is going to be the following, for example. It's going to be a naught plus a1x plus a2x squared. Right. We continue. Okay, let us check this one. So you're going to have that R. So in other words, you can do R3. You can write here R3 of x. Which is divided by right, which is divided by the following. So now you divide by a denominator of degree 1, but you see this denominator of degree 1 is actually written as follows. It's written as 1 plus b1x. 1 plus b1x. This gives okay, this is going to produce the difference R3 of x minus f of x, which is a naught plus a1x, a2x squared. You divide by 1 plus b1x minus f of x, which is x squared plus x cubed. So we continue. Right. So now we continue with the simplification here. If you have this, so in other words, this which simplifies to a naught plus a1x plus a2x squared. minus, if you cross multiply this thing, you have 1 plus b1x x cubed. Okay, so, and if you do this, you'd have to equate it to 0. If you multiply everything in the Pade approximation process, you'd have a naught, a1x, a2x squared, minus x squared, minus x cubed, minus b1x cubed, minus b1x to the 4th power equals 0. So this is what we have. This is exactly what we have here. So we continue with our analysis of this. So if we have, therefore, that this is a naught plus a1x plus a2x squared, right? So we continue. So we continue. Minus x squared minus x cubed. Minus b1x cubed. Minus b1 x to the power 4. So what exactly is this? This is exactly the same as the following. So there's going to be a factorization that we're going to do. So we have only one constant term, a naught. There is a1x, only one linear term. Then the quadratic are two quadratics, like a2x squared minus x squared, giving us a2 minus 1 x squared. The cubics are two of them, so it's minus 1 minus b1 x cubed minus b1 x to the 4th power. Okay, but obviously, I mean, this is equal to 0. Equal to 0 means it is 0 plus 0x plus 0x squared plus 0x cubed plus 0x to the 4th power. Which means, therefore, that a0 becomes 0. A0 becomes 0, which means that a1 becomes 0, a2 minus 1 becomes 0 for the quadratic, so which means minus b1, yeah, so you'd have exactly that. See, now you'd have x to the 4th power, so which means that a2 is 1, right, which means that our a2 is 1. Right, so you can just stop it. Because this f stops at x3, you can just stop at x3 and remove this one. Because you actually go up to x squared, x3. Highest degree is x3. So which means, therefore, that b1 is minus 1. So this x4 term you can just remove. So which means that b1 is minus 1, a2 is 1, a1 is this, a0, and a0 is 0. Hence, A0, A1, x, A2, x squared, you divide by 1 plus B1x. A0 is what? Is 0. A1 is 0. A2 is 1. Giving us x squared divided by 1. The B1 is minus 1. So, and this therefore means that hence the Pade, right? Hence the Pade approximation. The Pade approximation R3 of x is R sub 3 of x is actually exactly x squared divided by 1 minus x. So that would become the Pade approximation for this particular system. And we have got the answer, and we have got the Pade approximation, and we're excited because we have got the answer. And then we are ready to move on and to move forward to the next question, because we are just practicing here. We're just practicing here and making the most of our learning. Let's try the next question. Let us try the next question. Let us try the next question. Okay, there's a method we call the Adams-Bashforth method. The Adams-Bashforth three-step method. Adams-Bashforth three-step method. Right, it's a very, very interesting method, and I want us to spend some time today discussing this method together. But the Adams-Bashforth three-step method is a beautiful method that uses the method to approximate. For instance, the Adams-Bashforth three-step method is given by y sub 0 is alpha sub 0. Y sub 1 is alpha sub 1. Y sub 2 is alpha sub 2. Y sub n plus 1 is y sub n, etc. Apply this method to approximate y at 0.5 for the differential equation dy dx equals x squared, where x lies between 0 and 0.5, while 0 is 0, using step size of 0.1. And in other words, it means that our h is 0.1. And the first three approximations obtained from the second order Runge-Kutta method is this. Use 3 decimal digits with rounding at each step. So we continue. Right, so now if we continue with our analysis of this one, let us solve this particular past paper question on the Adams-Bashforth method. But first, we're going to look at the fact that y0 is alpha 0. So we start. Y0 is 0 for the fact that y sub 0 is alpha 0. So this is the condition. But now to get the next thing, the next step, we're going to use the second order Runge-Kutta method, which is this. This is the algorithm for the second order Runge-Kutta method. Meaning that when we want to get y0, we've got y0. So alpha 0 is 0. Alpha 0 is 0. Okay, we continue. Using the second order Runge-Kutta method in the Adams-Bashforth three-step method, we're going to do y1. According to this, y1, when n is 0, you have y1, which is going to be y0 plus half k1 half k sub 2. y1, y0 plus 1/2. So what is k1? K1 is going to be, according to this, k1 is h. Then you have f of, right, so the k1. But whenever n is 0, it's going to be x0, y0. Half k2 is hf, which is x0 plus h, y0 plus h, which means that according to the second order Runge-Kutta, y1 is going to be y0. What is y0? y0 is 0. So you put a 0 here. Half h is 0.1. So you put 0.1. Then you're going to have f of x0, y0. This is the f. So if this is a derivative, then it means that fxy is x squared. So which means that this is x0. So x0, according to this, it's going to be like x0 squared plus half h is 0.1. Then we have the f of this, but f of this, according to this, is going to be just the square of the first component, which is going to be x0 plus the h is 0.1. H is 0.1, and you square everything. Meaning y1 is the following. y1 is the following. So let us continue with our simplification of the second order Runge-Kutta method. Now at this point, what do you have here? So you have 1/2 0.1. Then we have x0. This is x0. So x0 is 0. x0 is 0, so you have a 0 squared. Okay, if for x0 is 0, so we have that x0 is equal to 0. So x0 is equal to 0. Okay. So therefore we have that x0 is equal to 0. Right, and then we have 1/2 x 0.1. What is x0? It's 0. So now, so then we have the following. Let's use a calculator. 1/2 you can punch. You can even use octave for this one, but okay, you can practice using octave, but yeah, it's easy for octave. Because the octave can be used mostly for systems. It's much more profitable than just numbers where calculator can easily be used. So we have 0.1, and then you square this. So, okay, this is, okay, the calculator is giving 1/2000. Okay, 1/2000 can be written as 5 times 10 to the power minus 4 in scientific notation. So which means that y1 is exactly that. But you can write it also as the 1 over 2 is 0.5. The 1 divided by 1,000 is 0.123. 1, 2, 3. Yeah. 1, 2, 3. So you'd have, anyway, let's just write it that way. It's okay. Let's just write it that way. It's fine. And then we'll continue with our analysis. Okay, yeah, that is y1. Then we need to get y2 by the Runge-Kutta. So we're going to have, for example, the following. Let's get y2 by, okay, getting y2 according to the Runge-Kutta, it's going to be, y2 is going to be y1 plus 1/2 fx1 y1 so of h fx1 plus h okay, let me see what we added here. Okay, because in K2 we must add this one is y0k1. So in the K2, so it's y0k1 y0k1. So we continue. But obviously, when you look at the f here, the fxy is just going to square only the x component. So that's why 0k1. So, but it's not going to affect anything. Let's move on. But now I said already, this is going to be x1 h and then y1 plus k1. Like this. So which means that what you have here is y2, then you have y1. What is y1? We've got that y1 is 5 times 10 to the minus 4. That's what this calculator gives. That is what the calculator gives using the Adams-Bashforth, 3-step Bashforth. So you have that, but yeah, it's 5 times 10 to the power minus 4. The 5 times 10 power minus 4 gives us the result we need. Right, so we continue. Right, so we continue with actually solutions pertaining the Adams-Bashforth method. And now I'm still in class, Shinki, and I'll give you a call when I'm done. Right, so good, Shinki. Right. So now we have y2, which is y1. Y1 is 5 times 10 to the power minus 4. 1/2 of the h is 0.1. And then now, if this is the case, we have f of xy is dy dx. So that now you have you square the x, which is so now if you have the f of these so now then you have the following, yeah? So you have the square there, because you only square the x, only square the x1. Okay, but yeah, you must be very careful because x1 is the next step. X1 is the next step. So, because if, according to the Adams-Bashforth, x0 is 0, x1 you add h, so it's going to be, you add 0.1. So it's going to be 0.1. So you add 0.1 and then you square it. Half of 0.1, x1 is 0.1, h is 0.1, and then you square everything. So you have this here. We continue. Which is 5 times 10 to the power minus 4 plus 0.5 by 0.5 is the 1/2 by 0.1 by 0.1 squared plus 0.5 by 0.1 by 0.2 squared, which is 3 over 1,000, 3 times 10 to the power minus 3. 3 times 10 to the power minus 3 is the y2. By the second order Runge-Kutta, then we must get, okay, we got y0, we got y1, we got, for example, we got y0 is 0. y1 is 5 times 10 to the minus 4. y1 is 5 times 10 to the minus 4. y2 is this one, 3 times 10 to the minus 3. So we got the 3 y values. We got actually exactly the 3 y values. We got the 3 y values. Okay, so these are like the initial values we've got in the Adams-Bashforth method, but it is already coupled with the second order Runge-Kutta. This algorithm is the algorithm for the second order Runge-Kutta. But now we continue with our analysis of this, and then we want to solve these completely. We want to solve these completely. So to solve this completely, we have a couple of things that we need to take into account. Right. So we continue. Right. So now, if we have the following, right. Let us continue with our analysis, please, and solve this particular problem. So the next thing is now we've got the y0, which is this one, y1, and then y2 is this one. Then now we're going to get a y3 using the Adams-Bashforth three-step method. But obviously, we need to apply this method to approximate y at 0.5. The y0 is this one. Y1 is y evaluated at x1. Y evaluated at x2, but y evaluated at x2 is like 0.2. Y evaluated at x1 is 0.1. Okay, so we want to find more. So now we want to find 3. Y at 0.3 using the Adams-Bashforth. So now using the Adams-Bashforth, then we're going to be in a position to do the following. So we're going to do y3, which is going to be y. It's going to be exactly the y2. Rather, it's going to be y3 here. When n is 2, then it's going to be 2. So which is 0.1 divided by h, divided by 12. 0.1 divided by 12. And this is f of the following. So if n is 2, then it's going to be x2, y2. Minus 16. F of, if this is 2, then it's x1, y1. Plus 5 of. If n is 2, then it's going to be 2 minus 2, and this is going to be x0, y0. So we're already done with the second order Runge-Kutta method, and then now we are using the Adams-Bashforth 3-step method. But now it's going to give us y3, but as we've already seen, it's y at 0.3, but we must go up to the 0.5. Okay. So now let us continue with the process. If you check, which is y3, which is exactly y2. Y2, which is 3 times 10 to the minus 3. (0.1) you divide by what? Divide by 12. This is fx2y2, but this is fxy. Fxy is the differential equation, dy dx equals x squared. So now you just square the x. So here I'll just square x2. What is x2? As indicated that x0 is 0. How do we know? Because of this, it is y at x0 is 0, but x0 is 0. x1 you add h, you get 0.1. x2 you add 0.2, you get 0.2. You get 0.2. You get 0.2. We get 0.2. Okay. We get 0.2. Okay, so now we have x2. So x2 is 0.2. x3 you add 0.1, you get 0.3. x4 is 0.4. x5 is 0.5. So you have this one, x2 is 0.2. Minus 16, we have x1 is 0.1. You square it. 5x0 squared, x0 is 0 squared. So this is our y at 0.3. Then we're going to use our calculator here with the Adams-Bashforth three-step method. Let's use our calculator to save time, but we can also use Octave as well. But these are just numbers, so it's easier with the calculator. So, but when you have systems of matrices, then it's easier with Octave. Right, so this is to the power minus 3. So plus 0.1 divided by 12. Right, 0.1 divided by 12, and then you have the bracket, then you have 0.2, you square it, minus 16 times 0.1 squared plus 0. Which is 1 divided by 500, which is 2 times 10 to the minus 3. Two times 10 to the minus 3. Let us do another one. So because we must apply this method to approximate y at 0.5. 15 marks. You get this one, you have passed the exam. Let us do y4. y4 is 0.4. y4 is 0.4. So if you have the 0.4, you're going to have the following. Okay, you put for y4, you put n equals 3 here. So it's y4, but it's going to be y3 plus h. You can put h if possible. So you can put h out of 12. fx3 y3 minus 16 f4. So if n is 3, 2 y2. N is 3, fx1 y1. So what is y3? Let us check y3. This is y 0.3, which is like y3, and y3 is 2 times 10 to the minus 3. So in other words, y3 is 2 times 10 to the minus 3. H is 0.1, you divide by 12. x3 is 0.3, you square it. Minus 16 is 0.2, you square it. 5, then you have x1, which is 0.1, you square it. So this is going to be y4, y at 0.4. Let's use a calculator. Y times 10 to the power minus 3. 0.1 divided by 12. 0.3 squared minus 16 times 0.2 squared plus 5 times 0.1. Okay, for the first time, it looks as if it is negative. We're going to check it. But it's minus 2.1 minus 2.166 recurring times 10 to the power. Let's check this one. So it's going to be times 10 to the power minus 3 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 like this, which you can approximate it as, which is y at 0.4, 2.17 times 10 to the minus 3. Right, so that is what we have. That is exactly what we have. So this gives us y4, but let's check this y4. Okay, we continue with our analysis, and once again, we check that according to the Adams-Bashforth, yn plus 1 is y sub n, etc., etc. But now if you want to get y4, which means that n is 3, it's going to be y3, kj of 12, and this is going to be 3, 3, and this is going to be 2, 2, because it's 3 minus 1, 3 minus 1, which is 2, and then this one is going to be 3 minus 2, which is 1. When you come to this pointer, we have our y3. Okay, we got down the y3 was 2 times 10 to the minus 3. 2 times 10 to the minus 3, which is plus 0.1 divided by 12. 0.3 squared minus 16 times 0.2 squared plus 5, 0.1. So now let us check with the calculator once more. So if, for example, you're dealing with 2 times 10 to the power negative 3 plus 0.1 divided by 12. 0.3, you square it, 0.3. So it's going to be 0.3 for the x3, 0.3 squared, minus 16 times 0.2, you square it, plus 5 times 0.1, you square it, then you close. So we got minus 13 over that, which is minus 2.16 6 recurring times 10 to the minus 3, which is minus 2.17 times 10 to the minus 3. And this is the answer. And this becomes the answer. This becomes the answer. Okay. So we continue with the next one. Right, in the next case, we're going to do the y, the last one. So we're going to do y5. Okay, because now we are doing the last one, 0.5. So we're going to do y sub 5, which is y at 0.5. According to the Adams-Bashforth, this one, three-step method, then we're going to have y sub 5, it's going to be y4. H divided by 12. If this is 4, this is x4, y4. Minus 16. Minus 16. F of, okay? So if this is y sub 5, then this is y4, it means n is 4. N is 4, you put here, you get 3. You get 3. When n is 4, you get 2, you get 2. So right now, if we have y sub 5, what is y sub 4? Y sub 4 is minus 2 times 10 to the minus 2 times minus 2.17 times 10 to the minus 3. And this is actually exactly our y sub 4. Right, so this is what we have. So which means that here we're going to have y sub 4, which is minus 2.17. Right. Minus 2.17 minus 2.17 times 10 to the minus 3. H is 0.1, you divide by 12. This F, because this one is the fxy is equal to this, so you raise it to the square. So it's going to be 0.4, x4, because we know that x0 is 0. According to this, we start from 0. But we're going to go up to 0.5. So which means that x1, we add h, which is 0.1, which is 0.2, is 0.3, is 0.4, is 0.5. X4 is 0.4. You square it. 16x3 is 0.3. And then x2 is 0.2. Right, and then now you'd get y sub 5, which is y at 0.5, which is what they want. Because it said apply this method to approximate y at 0.5. So the y at 0.5 is exactly what? It's exactly y sub 5. And let's use a calculator. So now this is plus 0.1 divided by 12. 0.4 squared. 16 times 0.3 squared plus 5 times 0.2 which is minus 4.5 times 10 to the minus 3. Minus 4.5 times 10 to the minus 3. Minus 4.5 times 10 to the minus 3. So this is what we wanted. Let us check if this is accurate. So to check the accuracy of this, we're going to use the following. So we might do minus 2.167 times 10 to the power minus 3, for example, plus 0.1 you divide by 12. Open bracket 0.4 you square it, minus 16 times 0.3 you square it, plus 5 times 0.2, which is minus 4.5 times 10 to the minus 3. So this is the same answer we have got. So in other words, use 3 decimal digits with rounding at each step. So obviously now using 3 decimal digits with rounding at each step, something that we actually quite violated. We did not really maintain that, but the 3 decimal digits would be 500, and therefore this will be 3 decimal digits times 10 to the minus 3. In which case, obviously, I mean, it was subject to that kind of analysis. So yeah, would have possibly obviously taken more decimal digits, but this is what we call the Adams-Bashforth 3-step method. That is used in conjunction with the second order Runge-Kutta method, which is y sub n plus 1 equals y sub n plus half k1 plus half k2. K1 is h, f of xn, yn, and k sub 2 is h, f of x sub n plus h, comma y sub n plus k1. So this is exactly what we have got there. So now, right now, we continue then with our analysis of this. So in other words, we've been able to approximate, because this question was apply this method to approximate y at 0.5. Y at 0.5 is y sub 5, which is minus 4, 5 times 10 to the minus 3. Minus 4, 5 times 10 to the minus 3. And we've had a chance to study one of the methods that is highly examinable and must be understood, what we call the Adams-Bashforth method. And obviously it's very important, therefore, that we are able to understand this method very well. Right, the method of Adams-Bashforth 3-step method is a very, very important method that must be understood. And Shingi, obviously, I'm here to call you when I'm done with my discussion. And yeah, I'm not yet done, but as soon as I am done, I'm sure that I will reach out to you so that we can be in a position to have a conversation. Okay. All right, good. So now this actually becomes exactly what we are noting, and what we need to understand, and this kind of method that we need to make sure that it's actually very much close to our hearts, but also it is a method we understand. Okay, I'm navigating through material here because I want to get another question to do. Right, because we finished with the Adams-Bashforth, but there are other methods that we need to learn, and we need to understand very well, and we need to learn for exam purposes. And I feel that we're gonna do on a lighter note. We're not gonna break our fingers or explode our brains. I'm actually looking at the amount of time left, so I want to practice a method that will be in the exam, rain or shine. Okay, here is a method that is going to be in the exam, rain or shine. This method is called the, okay, on a lighter note, I know it's very popular, but we're only left with like nearly 8 minutes or something like that. So I just want us to make sure that we recap on a method that is very popular. We can recap on other things. So we obviously I don't want a problem that is going to be very long. Right, for this one, for example, 7 marks. Let's just take note of the kinds of things we need to learn and the kinds of things we need to master about this particular problem here. So the method of the fourth order Taylor method, okay, it can be any order in the exam, but obviously I want us to just, you know, take it easy, refresh with this, because I'm just looking at the amount of time. I don't want to begin a problem that is going to be very long, that is going to take us way a lot of time beyond the time. But I want us to indulge and chill a little bit and have something easy. Something easy. Okay, we start. This one is dy dx is y squared, y at 0 is 1, and delta x is 0.1. We need to solve this particular problem. We test our problem solving skills on the fourth order Taylor polynomial. So now to note the fourth order Taylor polynomial, we know that we're going to have y at x. So y at x is the same as y at a plus y at a. And if it is that, y at a, we put a prime here and we multiply it by what? We multiply it by x minus a. We continue with y double primed at a. I know I might be using a slightly different notation, but the meaning is the same. And we have x minus a, and then you cube it. Okay, of course you're going to square it. Okay, I'm just doing this so that you can just master this kind of a method. Okay, because we don't have lots of time left. And then we have 1, 2, 3 at a, then we have x minus a, you cube it, and then it's going to be 3 factorial. Fourth order, then you're going to do the fourth one, which is y fourth derivative at a, then we have x minus a, you raise to the fourth power over 4 factorial. So you have y at x. Okay, we're going to do 1 because at 0.1 and 0.2, so we're going to obviously do this at 0.1. But obviously, noting that we're starting at this, so our x0 is 0. But obviously, then we actually obviously will add 1 step to this. So if we actually obviously are to add 1 step to this, then we're going to actually proceed as follows here. So the couple of things we need to take into account. So we want to actually evaluate these at 0.1. So let us do these at 0.1. So if you do this at 0.1, for example, because they're saying at this, so you're going to do it at 0.1. Right, if you do it at 0.1, then what will this be? Let's ponder on these and reason these together. So if it is at 0.1, you actually obviously right now are going to add the following. Because this is first at y at 0 that is given, it means that we must be able to get the y at 0. Then you would have y primed at 0. Right, y primed at 0. Right, if you do y primed at 0, then you would have x minus 0. Then you're going to do y double primed at 0 over 2 factorial. Then we have x minus 0, you square it. y triple primed at 0 over 2 over 3 factorial, x minus 0, you cube it, y to the fourth derivative at 0, then you have x minus 0, you raise it to the fourth power, you divide by 4 factorial, which means y at 0.1 is equal to y at 0. What exactly becomes y at 0? Y at 0 is clearly 1 plus, this is 1 here, this is y at 0 is 1, y primed at 0, so this is like y primed at x is this. Right, so now the minute you're going to do y primed at 0. So when you do y primed at 0, you're going to make x equal to 0. So it's going to be y0 squared, but y0 is 1, so it's going to be 1. And then you actually obviously will have to continue with this, but if it is exactly at the next x value, and you would actually obviously take note of the fact that it is at 0.1, yeah. So if it is at 0.1, then it means that you're going to do 0.1. Right. Right. We continue, which is y prime 1, and then you have 0.1. Then now you're going to have y double primed. Y double primed means that we're just practicing with this one. It's not a very difficult one, but we're just for master of this. So y double primed, y primed is this. So y double primed, you find the derivative of this. So the derivative of this now, you find y double primed, which is 2y y primed. Right, so y double primed is going to be 2y0 is 1. Y primed at 0 is a 1. You divide by, it's a 1. You divide by 2 factorial, and then there's 0.1. So let's do the third derivative. Y triple primed. Okay. So what would y triple primed be? So y triple primed would be 2y primed y. So now y triple primed, to find the derivative of this one. And then after you find the derivative of this one, you multiply with this. And then you have 2y. Then you find the derivative of the next one. So the y primed at 1 is going to be 211 plus 2y0, which is 1. Y double primed of 0. Y double primed at 0, we got exactly what? Y double primed at 0, you have y0, which is 1, and y double primed, which is 1, and it is 2. It is exactly at 2. So y0, so this one is 2. And then 2 times 2 is 4 plus 2 is 6. So this one is going to be 6 divided by 3 factorial, and then it is 0.1 cubed. Okay. 0.1 cubed. 0.1 cubed. Okay, let us do one more, the fourth derivative of this. So if this is the third derivative, what will the fourth derivative be? Let us do the fourth derivative, and then we are done. Once again, just practicing this method here of the fourth order Taylor. So which means the fourth derivative, so we can do 4 in parentheses, yeah? Right, we can do 4 in parentheses. Right, we can do 4 in parentheses. We can do 4 in parentheses. Right, so now, okay, we are continuing, please. We are continuing. Right, so now we're going to do the fourth one, which is the following. So it's going to be the fourth derivative, which is going to be, so the fourth derivative is going to be this one, is going to be 2y, second derivative y, 2y, okay, yeah, second derivative with this, and then 2y primed, and then 2y, and then you have this, and then you have 2y, 1, 2, 3. So if you have let us calculate the rest of these. So we continue as follows. Right. So we're going to have, okay, let's just calculate these things. So that y double primed is what? Y primed is 1. Y primed is 1. Y0 is 1. Y triple primed. Y triple primed, we got a 6. This is 2 by 2. It's a 4 plus 4 plus 4 plus, it's exactly 4 plus 4 plus 4 plus 4, 4, 4, which is the third 4. Okay, please wait in class until Lisedi. Okay, stick around, please. So we have 2 times 2, it's a 4, 2 times 2, it's a 4, 2 times 2, it's a 4. There are 3 4s, and then there's 2 by that, which is 12. So, and this is exactly 12 plus 12, which is a 24. So this one is actually 24 divided by 4 factorial, and then it is 0.1 to the 4th power. So which means that y at 0.1, which is 1 plus 0.1. So the 2 divides, which is 0.1, you square. 3 factorial is the same as 6, giving us 0.1 cubed. 4 factorial is the same as 24, which is 0.1 to the 4th power. So please stay in class, stick around, Lisedi. We are starting your discussion now. We're just finishing something here. So now, as a consequence, what then we are getting here is the following, which is 1 plus, you have 0.1, you square it, plus 0.1, you square it. Okay, there's no square here. There's no square here, so it's 0.1 plus 0.1 squared plus 0.1 cubed plus 0.1 to the 4th power, which is 1 point quadruple 1. Right, 1 point, it appears that we have 1 point quadruple 1. Let us check this out. Launching the calculator, we got 1.41. So which means that you have 1.41. 1.1234. So now the 4th order Taylor method will be this one for a total of 7 marks in the exam. Okay, yeah, this was just a closing discussion because I didn't want to start a very long problem. Okay, but now we discussed some of the methods, and I'm sure that you have seen a thing or two. Perhaps the Adams 3-step Bashforth method is the method that was new today, and the other methods, obviously, the use of the of octave to solve some of the problems. We're gonna do more octave in our next meeting, so you let me know when we can meet again. We can meet again tomorrow at the same time or during the week, whatever you let me know. I'll hear from you, and then we'll see what we can do. I mean, in terms of the time, you let me know. I'll depend on you so that we can have our next meeting. Right, I must thank you for joining us. It was awesome having this discussion. Until I hear from you again, obviously we're going to send the recording, but until I hear from you again, then I'll wait to hear from you on the next time meeting. Okay.
All right. Thank you so much.
Okay, thanks, dear. Have a good day and goodbye.
You too. Bye.
Thanks. Goodbye. Lisedi. Lisedi. Lisedi.